Students, today we are going to discuss chemical equilibrium. Now we are going to discuss the differentiation between reversible and irreversible reactions. Reversible, irreversible. Now we are going to reversible reactions, or the reaction which can go forward or backward. Irreversible reactions are the reactions which cannot go forward reaction, i.e. they are single direction reactions. Go in single direction. Reversible reactions are the reactions which can't complete. Can't complete. And the irreversible reaction can complete in any time. Can complete in any time. Now we are going to discuss the examples. Now we are going to draw the equation how it represents. A gives rise to B. This is the equation. Now A gives rise to B. Only single direction. Now there are a lot of examples. Now CaCO3 CaO plus CO2 in a closed vessel. Because in the closed vessel it can compete with CaO and forms CaCO3, and here CaCO3 gives rise to CaO plus CO2 in open vessel. Now we are going to discuss the equilibrium state. Equilibrium state. Now, equilibrium state is the state at which the macroscopic properties like color, concentration, volume, density, pressure does not change with the time. That when they are at equilibrium. Now, state at which macroscopic macroscopic properties like color, appearance, color, function, density, does not change with time. Now, there are two types of equilibrium constants: chemical equilibrium and physical equilibrium. Right. Chemical and physical. Chemical equilibrium is the equilibrium state which are chemical reactions. And chemical reactions. Physical equilibrium is the equilibrium state at which there are physical states. For example, between solids to liquids, there is an equilibrium. Conversion of physical quantities. Now we are going to discuss about characteristics of equilibrium. Now, at equilibrium, the rate of forward reaction and the rate of backward reaction will become equal. Rate of forward reaction will be equal to rate of reaction, and as mathematically it makes us as RF is equal to RV. Now, if we can express in graphs, okay, it is the first we will draw a graph for reactants, and for products it is the graph. It is the equilibrium state at which the rate of forward and rate of backward will become the same. It is for products, and it is for reactants. Now, as during the reaction, the reactants will decrease and the products will increase. Two, during a reaction, reactants will increase by products will increase. Now, as the reaction progresses, the rate of forward reaction decreases and the rate of backward reaction will increases. Rate of forward reaction decrease while backward reaction will increase. Now, chemical reaction is dynamic, but it is not stopped. But the rate of forward reaction and the rate of backward reaction will be the same at equilibrium, as we have discussed it here. Now, chemical equilibrium is dynamic in nature, but it is not stopped. But it is not stopped. But the rate of forward reaction and the rate of backward reaction will be same. And rate of forward reaction equal to rate of backward reaction. Now we have completed about equilibrium state and characteristics of equilibrium. Now we are going to discuss the next topic, that is laws of mass action. Now we are going to discuss about laws of mass action. Laws of mass action. Now we are going to discuss this statement by using an example. Now P plus Q gives rise to R plus S. Now they have the trigonometric coefficients N1, or they have the trigonometric coefficients 1 because they don't have any value. 1. Now, according to laws of mass action, the concentration is equal to the products of reactants whole raised to the power of their powers. Now, statement. It states that the the product of concentration of reactants raised to the power of raised to the power of their stoichiometric coefficient. Stoichiometric coefficient. Now, as stated above, now it is described as K. K is equal to P into Q. Here we have expressed in square brackets. The term that was expressed in square brackets is active mass of the reactants P, and another term that we have expressed in square bracket Q, that is active mass of Q, that in Q. Now we can write for products also. K is equal to R and S if they have coefficients as M P plus MQ gives rise to AR plus BS. Now, equilibrium is equal to loss of mass action K is equal to P to the power of M, Q to the power of N. This is this one. Now, it is dependent only and only on temperature, not on pressure, volume, and so on. Note, it is only and only dependent on temperature, Now, how the laws of mass action works at equilibrium. Now let us see how it works. Now we are going to discuss about K equilibrium. K equilibrium states that the ratio of K equilibrium of forward reaction and the K equilibrium at backward reaction. K forward divided by K backward. K forward means the concentration of reactants will be more, so we will choose the concentration of reactants. K backward means the concentration of reactants will be the more. Now we will choose an example. N1A plus N2B gives rise to N3C plus N4D. Now K forward. K forward means we will go forward. So K forward. K forward is equal to C into N3 into D into N4. Now K backward is equal to A whole to the power of N1 and B whole to the power of N2. So students, I have said that here K forward for reactants No. They are for products. Sorry. Okay. Now we will substitute this in this equation. C whole to the power of n3 and d whole to the power of n4 divided by a whole to the power of n1 and b whole to the power of n2. Now it is applicable only for gases. For solids, pure solids and pure liquids, the value of individual terms is unity, 1. Now we are going to discuss about if active masses are given in concentrations. If active mass given in concentration, then we will use the term Kc. Kc is equal to K equilibrium is equal to C whole to the power of n3 d whole to the power of n4 divided by a whole to the power of n1 and b whole to the power of n2. If active masses are given in terms of pressure, if active mass given in pressure, then it gives rise to Kp. Kp is equal to, here it will become Pc whole to the power of n3 and Pd whole to the power of n4 divided by Pa whole to the power of n1 and Pb whole to the power of n2. As we know that Pv is equal to nRT. P is equal to n by V RT. As we know that a concentration C is equal to n by V. It is replaced by C. So P is equal to CRT. Now we are going to discuss the relationships between Kp and Kc. Now we are going to discuss about relationships between Kp and Kc. Now we will write the formulas individually. Kp is equal to Pc whole to the power of n3 Pd whole to the power of n4 divided by Pa whole to the power of n1 and Pb whole to the power of n2. And we will write about Kc. Kc is equal to C whole to the power of n3 d whole to the power of n4 divided by A whole to the power of n1 into B whole to the power of n2. Now, as we have discussed earlier, that P is equal to CRT. In the place of P, we apply, in the place of P, we can apply CRT. Now, Kp is equal to C, we can common C C into N3 RT over to the power of N3 into CD over to the power of N4 RT over to the power of N4 divided by CA into N1 RT whole to the power of N1 into CB whole to the power of N2 RT whole to the power of N2. Now we will take this RT whole to the power of N3, N4, N1 and N2 into a single term. So this CC whole to the power of N3, CD whole to the power of N4 divided by CA whole to the power of N1, CB whole to the power of N2 into RT whole to the power of N3 plus N4 minus N1 plus N2. Now we know that this is Kc. Now we will write the relation as Kp is equal to Kc into Rp whole to the power of. Now this is written as delta N for it is only for applicable for gases. Delta N G. Delta N G. This is the relation between Kp and Kc. Okay, students. Now we are going to discuss the equilibrium constant. Now we are going to discuss the characteristics of equilibrium constant. Characteristics. First, it depends only and only on temperature. It depends only and only on temperature. We will see about this only and only on temperature in future chapters. Now, how the effect on stoichiometric coefficients. Now, effect on stoichiometric coefficients. Now we will make an equation, the simple equation. N1A plus N2B gives us to N3C plus N4D. The equilibrium. K equilibrium is equal to C whole to the power of N3, D whole to the power of N4 divided by A whole to the power of N1 and B whole to the power of N2. Now, if N3C plus N4D comes from left hand side, now we will see how it affects. Now, N3C plus N4D gives rise to N1A plus N2B. Now, K equilibrium is equal to here A Here new equilibrium Ke dash whole to the power of n1 and b whole to the power of n2 divided by c whole to the power of n3 and d whole to the power of n4. As you compare this here c and c, now we can conclude that K equilibrium dash is equal to 1 upon K equilibrium. Now we can conclude that if the psychometric coefficients are reversed, now the equilibrium constant will be inverted. Now if you multiply any one, but suppose if you multiply this, we will write here by a factor of 2 n1, for instance 2 n1 a plus 2 n2 b raised to 2 n3 c plus 2 n4 d. Now K equilibrium is equal to c into n3 d into n4 divided by a into n1 b into n2 whole square. Now it will become K equilibrium double dash is equal to K equilibrium whole square. Now as you see here, if we multiply the psychometric by any whole number, it will come to the power. Now we are going to discuss about partial pressure and Dalton's law. Now partial pressure and Dalton's law. Now partial pressure and Dalton's law gives the partial pressure of the individual gases. Gives the indivisible pressure of gases in the mixture. Now, according to Dalton's law, at constant volume and temperature, total pressure is equal to the sum of individual pressures present in the gaseous mixture. PA plus PB plus PC plus PT. We have assumed there are 4 gases. Now P of a particular gas is equal to the pressure of total gas into mole fraction. As we have discussed, mole fraction is the number of moles of that particular gas divided by total number of moles. P of gas is equal to mole fraction into P total. It is written as like. Now, this one. Now we are going to discuss how they are divided, how the pressure of the gas divided. Now, as we know that mole fraction is equal to N of gas divided by N total. Now, so students, now here P1 for gas 1, it is N1 divided by N total into P total. Now P2 is equal to N2 by N total into P total. For P3, gas 3, it is P3 is equal to N3 by N total into P3. Now we are going to write the ratios. P1 is to P2 is to P3 is equal to N1 is to N2 is to N3. As we have discussed here, the pressure of the individual gases is divided in the ratio of the number of moles. Now we are going to discuss the next topic and the last topic of today's session. Now we are going to discuss the reactions with delta NC, that means number of products, stoichiometric coefficient of number of products, because stoichiometric coefficient of number of reactants. Reactions with delta NC is equal to 0. Now we are going to follow the moles method. First, mole method. Now, if we take an example that 2Hi is raised to H2 plus I2. Now, at time t is equal to 0, at time t is equal to 0, the Hi concentration is R, that means reactants, and the products and the rate of H2 and I2 initially is 0 because they are not formed at time t is equal to T. It is R minus P. Here P by 2 because the stoichiometric coefficient is 2. Here is 1. This one we want to divide by 2. P by 2 and P by 2. As we have seen, K equilibrium is equal to H2 I2 divided by Hi whole square, because it is 2I. Now it is P by 2 into A by 2 divided by R minus P whole square. Now it will become as P square divided by 4 into R minus P whole square. Okay students, now we are happy. Now it is Kp because we have given the Kc. Here it is Kc. K equilibrium is equal to C is equal to Kp because delta Nc is equal to 0 here. Now Kc is equal to Kp is equal to this term P square divided by 4 into R minus P whole square. Okay students, that's all for today. Thank you for watching this video.